Good evening, everyone. I'm going to be presenting our securing UTM airspaces through adaptive zero trust architecture, and I'm joined by my colleagues, Shrivant, DJ, Carlos, Nick, and myself, Brody. So the first thing is our core problem and solution, which is that securing UTM airspaces through adaptive zero trust architecture. Our current UTM systems cannot scale because they rely on static security and implicit trust zones that allow attackers to move laterally. Legacy rules simply cannot adapt to dynamic mission factors like weather or location, so the solution is zero trust architecture, which is a superior approach that is designed for these real-time security demands. Next is our market crisis. Um, Adopting zero trust is a mandate. It's really not an option. We face a critical market crisis. Um, Commercially, weak security destroys public confidence and risks financial health. And then nationally, we are very exploitable, and our systems invite surveillance and sabotage. These securing airspace is essential for both our economy and our national safety. And for the future of UTM, it is at risk from unsafe management, which can lead to financial loss and weaponized aircrafts. Zero Trust is the necessary future-proof solution because it is cost-effective, scalable to any environment, and adaptive enough to handle rapidly changing tasks. And I'm going to hand this off to my colleague, Nick.
Hi, I'm Nick. I'll be talking about major security threats to UTM functionality and how Zero Trust mitigates each of them. UTM's exposed at every stage of operation, which gives attackers multiple points of attack. Zero Trust addresses these gaps through continuous identity verification, least privilege access, and encrypted communication. This table breaks the threats down individually. First, pilot impersonation. This falls under spoofing and affects U2 flight authorization. If an attacker poses as a pilot, they can submit or alter flight plans. Zero Trust prevents this by enforcing attribute-based access controls and requiring mutual TLS so identity is continuously validated. Next, manipulation of diagnostics. This is a tampering threat that disrupts U3 tactical deconfliction. Zero Trust mitigates it with cryptographic protections such as RSA key exchanges and AES encryption, which ensure that telemetry and position data can't be forged. The third threat is abnormal traffic, a denial of service threat against USS availability. Traditional systems frequently accept unauthenticated traffic. Zero Trust defaults to denying untrusted requests and uses IPS-backed firewalls to filter malicious traffic. Fourth, profile pattern recognition. This linking attack targets the public trust layer by analyzing exposed use-based data to infer system behavior. Zero Trust reduces these exposures through layered data protections and threat hunting tools. Finally, flight data sharing, a disclosure threat. If metadata is exposed, attackers can learn sensitive operational details. Zero Trust enforces full encryption and secure key management to keep this data confidential. Next slide, please. Now moving to the Linden model, this re-examines the vulnerabilities from earlier with a focus on privacy. Attackers can still exploit metadata, outdated systems, or predictable patterns, even when core services are secure. This violates the Linden categories of linking, disclosure, and non-compliance. Zero Trust limits exposure of sensitive data and enforces compliance to remove these blind spots. Next slide, please. Here we visualize the full escalation path in a traditional UTM system. The attacker starts with reconnaissance, identifies static credentials or unverified internal traffic, and launches a targeted authorization attack. Once inside, they escalate privileges because the system doesn't revalidate authorization. This leads to credential reuse and long-lasting sessions that never expire. From here, the attacker can manipulate flight plans or telemetry because no new authorization checks are triggered mid-operation. A second branching point appears when internal systems implicitly trust one another. This enables lateral movement, service impersonation, and spoof telemetry. A third weakness occurs when internal APIs lack mutual authentication. This allows context-free authorization, letting attackers inject false data or modify operational messages. All of these paths converge on operational exploitation, persistent access, and evasion. The core issue across the tree is the same: static rules, implicit trust, and missing identity verification. Zero trust collapses each stage by enforcing continuous authentication, mutual verification across all subsystems, and strict segmentation that prevents lateral movement. I'm going to be handing it off to Shrivanth to explain our DFDs.
Thank you, Nicholas. Hi, everybody. My name is Srivant. So we chose a specific portion of the UTM, the entire, service. So we specifically picked the tactical phase activation during the flight segment of UTM based off of the ConOps document that we had received earlier in the semester. So this is kind of just a quick overview of what it looks like, what we think it looks like before we implement our solution, and then I'll show you what it looks after. So some key things I want to point out: static authorization. So the operator is allowed to, once they log in, they have there's no continuous checks, and their credentials are valid for a time period that's longer than they need necessarily, because all they're doing is requesting an activation. Everything else is handled by other users, other actors, and like that. The next thing is session persistence. Again, inadequate session revalidation gives adversaries longer lasting access. So if this was an internal threat actor, he would or she would have more time to do things that they should not be doing. Implicit trust zones. You can see that this trust boundary is kind of encapsulating all aspects of tactical phase activation, and the trust within that, it leads to a lot of lateral movement. And then finally, authentication gaps. So a lack of mutual authentication allows spoofing of vital functions, like from telemetry to also just user credentials and things like that. Our proposed solution. So first thing right off the bat, you can notice that the trust boundaries are separated, and we added a couple of things. We added a policy decision point and identity access management process up here, where the operator has to kind of connect to, and then the PDP decides, hey, do we approve or disapprove this connection based off of things like IP addresses and things like that. The continuous monitoring and analytics process. So this will log all data and any sort of interaction within the system, from anything that happens with the UTM service provider to the login information from the UAS operator, as well as anything that the other policy decision engine creates down here. This is just for transparency's sake, so we know what's going on within our system, and then you can kind of implement algorithms to kind of determine, hey, are these normal or irregular actions that are being taking place. And then finally down here we have another policy decision engine. This is specifically to set the attribute-based access controls for each operator depending on the U plan that they are requesting and getting approval for. So, what's the flight plan? Is there any restricted areas? Height, things like that, or altitude, sorry, better word. And then, yeah, that is our final DFD. I'm going to now hand it off to DJ. Oh, sorry, Carlos, I'm sorry.
That's okay. Thank you. Well, I'm Carlos Ortiz. I'm going to be talking about a little bit about the demo we did. We divided everything in three parts. The first one is going to be the multi-factor authentication for the drone operations portal. Right now, as we were explaining before the improvements, our drone operations portal relied on a single factor authentication, which created a fundamental identity weakness across the entire UTM system. The problem was that the system implicitly trusted anyone who knew a username and a password. That meant several attack vectors were possible. For example, credential thefts, password reuse, brute force attacks, and no assurance that the person logging in was the legitimate operator. But the idea is, how can we eliminate all this? Well, to eliminate all this, we implemented a multi-factor authentication. Shrivan, if you can play the video so they can see. As you can see on the portal, we have already what was in the beginning. Basically, an operator is going to log in with a username and a password. But to add the extra layer of protection, we're gonna ask for like an additional factor, an additional verification step that in this case is gonna be 6-digit code. Give me 1 second. There we go, a 6-digit code. Basically creating like an extra layer of protection for the system. So this upgrade aligns with the zero trust core idea that is never trust, always verify. We also enhance the login portal with some enforced session timeout, IP login, encrypted connections, and a standardized security banner communicating IAM compliance. Together, these measures transform authentication from a weak perimeter checkpoint into a robust identity boundary that reduces the attack surface. You can move to the next one. Thank you. The next part of this demo is about the continuous monitoring. Originally, the system suffered from a major lack of visibility. Drone activity, operator requests, failures, and anomalies were occurring, but not in a way that could be centrally monitored or correlated. The previous setup had several limitations. Logs were distributed across components, making investigations slow. There were no real-time alerting meant outages or security events could go unnoticed. Also, there was no behavioral baseline. Sorry, no behavioral baseline, so abnormal operator or drone actions were invisible. Also, response times, request volumes, or system load were not tracked, limiting the performance insights. What we're planning to do, which is a continuous monitoring system, fix all this by acting as an integrated observability layer. And it's something you can see on the video that has been passing by. First, we have the real-time operation metrics. We also have a system activity visualization, which is basically a 24 hours activity curve that helps identity suspicious of our activity or perform anomalies. We also have a log aggregation and categorization. Basically, every event, mission completion, battery alerts, connection timeouts, weather warnings, etc., everything is going to be captured in an instructed timeline. Also, we have a complete API traceability that we saw on the last part of the video. Basically, every request that includes, for example, the methood, endpoint, actor identity, status code, etc., everything is going to be logged. And thanks to this, we are allowed to detect, for example, unauthorized commands, excessive request rates, which prevents possible DOS behaviors. We can also detect operator misuse and another kind of threats. So basically, with this upgrade, the UTM environment shift from operating blind to operating with continuous data-rich situational awareness, which is a core requirement for the zero trust systems. Please, the next one. And for the last part of the demo, I'm going to be showing the policy decision engine. So the previous version of the system used static, manually configured rules for restricting drone operations. This created multiple problems, like authorization logic was discarded and inconsistent. Also, policies couldn't adapt in real time to context, like, for example, the altitude, the time, the zone, etc. Also, operators sometimes had more privileges than necessary, which violates the least privilege. Also, modifications weren't tracked, leaving gaps in accountability. And there was no mechanisms to automatically enforce airspace rules. So the new UTM policy we're showing solve these issues by centralizing and automating all authorization decisions. As you can see on the decision policy engine on in the demo that is on the video, we can see different U plans. Basically, this define the mission levels, such as like restricted airspace windows, emergency service priority, and delivery route parameters. We also have different policies control that we will see in a second in the next part. Yeah, that is basically the attribute-based access control and the role-based access control. For example, let's say that a drone is flying below 400 feet in a restricted zone during peak hours. We can automatically deny the entry based on the sorry, based on the ABAC policy that on the attribute-based access control. So, and, oh, sorry, could you go back? Thank you. Sorry, thank you. And well, just to close, because yeah, we can continue. So this transforms, or this last part, the policy engine, this transforms the system from a loose collection of rules into a coherent, highly adaptive enforcement engine capable of responding dynamically to mission and airspace requirements. And thank you. That's all for me. And I'm gonna pass the next part to DJ to continue with the presentation. Thank you.
Thank you, Carlos. I'll go real quick since we're running out of time. But for a future outlook of our solution, the implementation performance and the overall future is important to consider. The implementation of this user interface where it's easy for operators and air traffic controllers to see what's going on and see the continuous monitoring is very important, while the various components will be computationally taxing. So that's a kind of a trade-off for our solution. And the future of this is that it provides more of an abstract and scalable solution that, regardless of your understanding of zero trust or cybersecurity, you can interact with it and make sure that you know what's going on in the UTM environment you're interacting with. And I'll hand it over to Srivant for a detailed test case.
Good evening, everybody. I just want to go over a quick test case of how this kind of works. So I'm going to talk about John Doe. He's a UAS pilot. He's flying on a company interface, so I'm assuming that it has some sort of protected TPM. So the actual interface itself is secure and throughout its whole life cycle and as it's being built, manufacturing cycle. And this instance is John wanting to log in and getting approval of his U plan so that he can, take off and do his thing. So the first thing he does is he's going to attempt to, interact with the IAM service and, oh, sorry. So he's going to type in the website, whatever the link is, and the IAM service will act as a gatekeeper and using some sort of IP whitelisting to prevent, to make sure that, John Doe, even though he hasn't logged in yet, should be, using this website. This is just a good way of kind of, some extra added protection. So once he logs in, obviously we saw in that video some sort of multi-factor authentication, either it be from an authenticator app or like an actual piece of hardware. So once that happens, a secure encrypted channel to all host services and is created, and all that login data gets immediately sent to the continuous monitoring and analytics service. After that, he can now send a request to activate a U plan. The database will respond and send that U plan to the correct service provider, and the service provider is at that point is going to create a response, and all these responses from the database and the UTM response as well is also going to be logged in the CMA service. Finally, this activated U plan is sent to the flight session policy decision engine. So using some sort of custom flight algorithm that we haven't really, it really depends on the nature of the drones and everything. It'll decide what rules to apply based off the U plan, and the also RBAC stuff based off of what kind of user John Doe is specifically. And again, these rules are logged, and then once it's all been activated and approved, ATC also receives that U plan, and then the U-Space services are finally uplinked to the actual drone. And from there, you can go on to the next parts of flight. And then one more thing, I want to talk about the actual overall risk of implementing ZTA. So the complexity in the PDP algorithm may lead to false positives. So this is the policy decision point for deciding whether someone logging in is a threat or not. There's a lot of data that gets ingested, and this obviously gets tailored based on the exacts of the UTM service. But this can cause bottlenecks, and in the end, it is a scaling issue. ZTA, all a ZTA really does is contain threat actors. It's not necessarily a protective barrier against all malicious activity. So still vulnerable to DDoS attacks, and there are other things we have to implement to protect yourself against that. And again, this intense logging system causes difficulties in analysis during audits because there's just so much information to comb through. So especially where time is sensitive, like during forensic accounting right after a cyber attack, going through these logs and figuring out what's pertinent and what's not may take longer than anticipated. And then finally, overall difficulty of implementing ZTA principles with legacy systems. This mainly means like where the drone operator is operating from. I'm assuming they're not, on their home laptop, or even if it is like a configured device, there are specifications and limitations that the device has. In order to, the trade-off is that it is protected. So there could be possible difficulties just integrating with that. And I'm going to hand it back off to DJ to kind of round us out.
Thank you. To conclude real quick, zero trust architecture, very complex approach, but our solution is very simple yet it provides many back-end layers to reinforce the areas that we're lacking in the legacy systems that we mentioned before. So our solution in general provides a user-friendly way for managing a secure UTM environment. And that's it.